Magnetic field due to a loop of wire. Consider a current carrying loop of wire of radius A. The loop is in the YZ plane. Here's the y-axis, here's the z, and the loop is in that plane. The radius is A, and it is centered on the x-axis, which is pointing out of the page and kind of to the right there. Find the magnetic field at point P, which is a distance x from the center of the loop, and a distance r from every point on the loop. Right, this point P, wherever you are on the loop, it's r distance away. We're going to use the Biot-Savart law to figure out the magnetic field. As we've done before, we'll start by calculating the magnetic field due to a small segment of the loop, ds. ds is up here. And it's in the direction of the current I. So here's Biot-Savart. dB, which is the magnetic field at point B, point P, due to that piece of the loop there, ds, is perpendicular to each ds and to the unit vector r hat, which is drawn between ds and point P. So here's r hat pointing along this line from ds to point P. We'll then resolve dB into its components along the x-axis and the y-axis, and we'll call them dBx and dBy. It's hard to visualize 3 dimensions on a piece of paper or a slide. And even so, when you have to draw it, it's hard to draw it too. So we're going to just rotate this guy in that direction. So we have the x-axis here, okay? And then this will be the y-axis. So the xy plane will now be in the plane of the slide. So our wire loop now is this thing over here to the left. We've got the current coming out of the page here, circling around and going back in at this point, which is the point where we're taking ds. ds is out of the page up here. Here's r, and r hat is along the line. And here's our dB. Notice how it's perpendicular to r hat, which is good. And then we'll resolve it into dBx and dBy. And here's our angle theta, which means this angle here is 90 minus theta. Since this angle here is a right angle, 90, theta shows up again over here. We did a similar problem when we wanted to calculate the electric field at that point due to a ring of charge. And we used symmetry. In that case, there was no perpendicular component of the electric field at point P, as it was canceled out by charge segments that were opposite each other on the ring. And guess what? We have the same thing here, right? If I take a piece here, if I take a ds there, compared to this ds, what we're going to have is dB is in that direction, so our dBy's will cancel, and the dBx's will reinforce each other. Same symmetry. It's the same symmetry, just a tiny bit different. Notice where dB is. It's over here, and we still get the dBy's canceling out as shown on the previous slide. But when we did the electric field was in the same direction as r hat. For the magnetic field, it's perpendicular. But since it works the same for over here, we're still going to cancel out the y components. So our magnetic field at point P will be along the x-axis, through the center of the loop and pointing to the right. The field lines, of course, we just don't have the one vector here. When we sum it up, the field will be this way. It will circle around, and I've run out of room, but it will certainly come back in this direction from the other side. Let's work with the vector cross product of the Biot-Savart law first. Since we have ds, the vector ds, perpendicular to r hat at every point, we use a definition of the cross product, which is the magnitude of each piece there. So it's the magnitude of ds, which is just ds. The magnitude of r hat is 1, and we take the sine of the angle between them because it's a cross product, and we get ds. We then note each current segment is the same distance r from point P. And what is r equal to? Well, a squared plus x squared, and you take the square root of that, Pythagoras. So we're going to take those values and plug it in to our Biot-Savart magnitude equation, because we've already found the direction of the field. We're just looking for the magnitude now. Here's Biot-Savart. We take the I out, put it in front, that's a constant. we found that ds cross r, the magnitude of that, is just ds. And we found r is the square root of a squared plus x squared. We square that, and we get this term. So that's the magnitude of this right here, dB. We've already said that the y components will cancel out, so we only need dBx. And that's going to be, remember we found this was theta? That will just be dB times cosine theta. And what's cosine theta? Well, we go back to this triangle, the first triangle, because it's the same theta, and realize it's adjacent over hypotenuse, so it's a over the square root of a squared plus x squared. Almost done. Here's our dBx. We put in dB, that's this term from the previous slide, and here's cosine theta. And then in the denominator, we have a squared plus x squared times the square root of that, and that's just a squared plus x squared to the 3 halves. And on top we have a, and we have ds, and our constant out in front. Now we're ready to integrate around the loop to find the total magnetic field due to all the little pieces of charge, pieces of current there, ds. This line integral is actually very straightforward, because when you add up all the little segments of a loop, you just get its circumference. That's where the symmetry comes in. So here's our long expression for dBx, and we're going to integrate that. We're going to do a line integral around ds. All these other things are constant, so we pull them outside the integral. We do the line integral, and we get 2 pi a is the sum of all the little ds's. That's just the circumference of our loop. And then we do a little more algebra, and here's our answer for the magnetic field at point P due to the current carrying loop of wire, and it is in this direction along the x-axis. Let's graph the magnetic field due to this loop of wire. Here's our equation that we got from the previous slide right over here. And where is this going to be a maximum? What's the only thing I can vary for a given loop with a radius a? Well, I can vary how far away you are from the midpoint of the loop. So if I want the maximum value, that occurs when the denominator is the smallest. So that would be when x is equal to 0. So that's this point right here. You plug that in, and your B max is mu 0 I over 2a. Now, what happens when you get farther away from the center of the loop? Well, we're going to assume as we get farther away that x will get much greater than a. A is fixed. So if we look at our equation on the left again, and let me just erase some of this. If x is really big compared to a, we can get rid of this term. And then we have x squared to the 3 halves is just x cubed. We have to leave the a in the numerator because there's nothing else to compare it to. There's no variable to compare it to. So we get this as we get farther away from the center of the loop. And you can see, hopefully, that that falls off rapidly as a function of 1 over x cubed. There's a similarity to the magnetic field at the center of a current-carrying loop of wire, which is what we've just gone through, and here's our loop of wire. At the center, we found that the magnetic field is mu 0 I over 2r. The magnetic field at a distance r from a long current-carrying wire, that's the magnetic field at this point, is mu 0 I over 2 pi r, different only by the pi there.